Hi everyone, welcome to an introduction to neural networks. So I'm gonna first start by talking about reviewing regression, logistic regression, multi-class logistic regression, and then finally, which are the simplest neural networks, and finally talking a bit more about the intuition behind neural networks. So these linear regression, logistic regression, and multi-class logistic regression are the simplest neural networks. So let's start talking about them. So as you guys have studied before, so here's an example of a linear regression model. So we have our x here is the square footage of a house and our y is the value of the house. And we want to model this problem by basically assuming that our prediction is a linear model of the square footage of the house. So we say our model is b0 times b1 times x, b0 plus b1 times x. And so here in the particular case, x is just one dimension. So b1 will be one number and b0 will be another number. So we're going to have two parameters in our model. So how do we find b0 and b1? We want to find the line that minimizes the sum of square errors. And so this is basically kind of a summary. So we have a loss function, which is the square mean square loss function. We have a cost function, which is basically the mean square loss function over trained data. And so this is our summary of linear regression. So now in logistic regression, what we have is that we have two labels. In this case, 0 and 1. So it's a binary classification problem, and we want to find the line that separates these two labels. In this case here we have like our in this little image here, our problem is two-dimensional, so I have x1 and x2, and the line is gonna divide the triangles from the squares. So our model for logistic regression, what we have first kind of a linear model, so a line, and then basically we take a sigmoid of that to predict the probability of the class 1. So in here we're gonna have, for this particular example, x will be two-dimensional, so b1 times x will be a dot product between a vector b1 and x, and b0 is going to be just one number, the bias, and then we're going to take the sigmoid of that to get a probability. That would be our model. So the sigmoid function is a function that basically takes a real number coming from that line and give us a number between 0 and 1, which you basically interpret as a probability of 1, of the class 1. So and then basically to optimize this problem, as we have talked in the past, we use the log loss function. So there is a similar problem, which you guys probably have heard of before, which is the multi-class logistic regression. And in this setting, we have k classes, and for example, we could have an image of the dog, and we want to predict the breed of the dog. So, but there is just one dog per image, so there is just one class per image. This is a generalization of logistic regression, and in this case we are gonna have so our y hat is gonna be the probability of each one of these classes of dogs, and basically it's gonna be a k-dimensional vector, and these probabilities are gonna sum to 1. The loss function that we're gonna use is log loss, which you guys have seen before, and this is the formula. And basically the model itself is gonna be, we're gonna have k equations. So we're gonna have gonna have z1 is equal to b1 plus w1 times x. Here w1 is a vector, the same size as the input vector x. Okay, so I'm gonna have k linear equations. To get probabilities from those linear equations, we're gonna use a softmax function, which we have talked about before. So what softmax is doing is taking each of these zk elements and exponentiating them. So taking the e to that to get a positive number, and then to get a probability you have to divide by the sum of all of the exponentials, and that will give you a probability. Okay, so that's how we basically work with multi-class logistic regression. So now these equations can be rewritten easily in a matrix form. Okay, so now z is a vector, a column vector, with elements z1, z2, zk, right? B is a vector, b1, b2, bk, and wi's will become the rows of w, a matrix w, which is, this matrix w is k times d. So basically then that simplifies in a way our equation. So we have one equation which is z equal w times x plus b, and this is how we can write, say, multi-class logistic regression. So we have a linear transformation followed by a softmax transformation. So that is a multi-class logistic regression. Okay, so now let's try to talk about what is actually a neural network. Okay, so let's go back. So this is multi-class logistic regression. Okay, so what a neural network is you can think about it as a stack of logistic regressions in some way. So if you think about it, so the first thing we do is that we take a linear transformation on the input variables x, and we call that z. Okay, and then we're gonna apply a nonlinear transformation to that z1, kind of similar to this multi-class logistic regression in which we apply to z a nonlinear transformation. So here we apply a nonlinear transformation. This is a function h that we apply element wise to z1, and then we're gonna take the output of that, this output a1, and we're gonna have another linear transformation. Okay, and now finally we're gonna have a prediction. Now this prediction is gonna be different whether we are working with regression, logistic regression, or multi-class logistic regression. In the case of regression, this z2, this is gonna be our prediction in the case of regression. Now let's look at how we define a two-layer neural network for binary classification. So we're gonna do the same thing. So we start with x is our input. We apply a linear transformation to that input. Then we apply to that a non-linear transformation to the output of this linear transformation. To the output of that, we apply a linear transformation again, and then after that we apply a sigmoid function. For the case of binary classification, z2 has to be in one number, so that then we apply a sigmoid function to that number, okay, to get a probability. Finally, how would we define this for a multi-class classification problem? So as you can see, this is very, very similar to what we did to the case of multi-class logistic regression. So first we apply a linear transformation, then a non-linear transformation to the output of that, then another transformation, and finally a softmax at the end of that. So what is a neural network? A neural network is, in a way, one way to think about it is that we are stacking logistic regressions on top of each other. So in the first layer, we go from having an input to having a basically to doing a linear transformation that give us some numbers that we apply a nonlinear transformation to. And then on that input, we have another linear transformation. And then finally, we apply some function that is going to give us either one number with a probability for binary classification. It's going to give us any number if we want to do regression, or it's going to give us k probabilities if we want to do a multi-class classification. Okay, I'm going to go and give you some intuition about these neural networks in the next few slices, and then we're going to come back to these equations later. Okay, so okay, first I am going to give you this example for later, so I would like you guys to compute to use these particular values to compute y hat. So basically to work with these equations to compute z1 and z2 and a1 and a2, and basically at the end to compute y hat. Okay, so go back to the equations and try to fill out this table here. Okay, so in the first few slices, I am going to use some visualizations from my friend Luis Serrano, and I just wanted to mention that he has a lot of very interesting videos talking about neural networks and mathematics and AI and machine learning, so which you should check out. He's a very good speaker. So suppose that we have you work for an admission office, right? So and you are in charge of providing a model to decide which students should go into the school. And you have to simplify the equation. Let's say that we have two numbers, the result of an exam and the grades so far from this particular prospective student. So here are some examples of what so there is a student 1 that has 9 out of 10 in the exam and grades 8 out of 10, and that student was admitted to the school. You have a student 2 which have 3 out of 10 in the exam and 4 out of 10 in the grades, and that student was not admitted. So my question is, would you admit student 3? So you have student 3, he has 7 out of 10 in the exam, we have grade 6 out of 10. Should you admit that student or not? So, and here are some potential functions you can come up with. For example, you can say, well, I am gonna sum exams plus grades, and if the score is bigger than 10, I'm gonna admit that person, and otherwise I won't. You can say, well, actually grades are kind of maybe more important, so I'm gonna instead do a score that is exam plus 2 times grade, and if that score is bigger than 18, I'm gonna admit. Or basically, or you say, you know what, I am just gonna admit either, if a student had the exams with a score bigger than 5 and the grade with exams bigger than 5. Okay, so these are possible functions that you can come up with. So in the first case, basically we have a line that will divide the first example, it would be kind of a line dividing the students on the top of that line will be admitted, and underneath that line will not be admitted. In the second case, we will have a different line that will also decide whether a student or not will be admitted, and students below the line will not be admitted, students above the line will be admitted. So our student will get accepted in this particular model, because it's gonna have in this case it's gonna have the exam bigger than exam and grades over that line, so that student will be admitted, right? So now suppose that you have a student 4, and that student has 10 on the exam but 0 in grades. According to this simplistic model we have here, this linear model we have, that student would be admitted. But it would be kind of weird, right? Having like 0 grades and 10 on an exam. Kind of sounds a little bit fishy, right? So maybe actually we don't want to really admit some of these points in here, the ones I am circling in black. Maybe actually we want to get those points out. So maybe what we want is more a non-linear boundary. So logistic regression is always going to give us a linear boundary. So basically what we want is a non-linear boundary. So these blue points here are going to be admitted and the red points are not going to be admitted. So maybe we want something like this. Okay, so how can we get this type of boundary? So that's the question. So how do we get non-linear from linear? That's another way of thinking about this question. So for example, this example here, exams bigger than 6 and grade bigger than 4, that is a non-linear function. So that for that you need kind of this kind of corner square, and that we cannot get from one linear boundary. So let's think about the following way to think about neural networks. So suppose that you have 2 professors judging these these inputs, right? So you have a college professor of English and another professor of math, and they have different ideas or different lines that they have on how to judge if a student should be admitted or not. So the judge one, the English professor, is going to have a particular function that he's going to use, or line that he's going to use to define if a student would be admitted or not. And then you have the math professor who thinks that other things are important, and he's going to have a different line or a different function different line that would divide these admitted students versus not admitted students. And then you have a president, or maybe another kind of the head of the committee, who is going to then say, well, if both of these judges admit, then I admit again as well. If they both admit, then I will admit. And that's going to be how I would define my function. So a neural network, in some ways, the way to think about it is that you have these judges, and the judges have some linear decision boundaries. Okay, and judge 1 is going to decide for his boundary, his linear boundary, and judge 2, he has his own linear boundary. And then there's going to be this president that is going to combine by another linear boundary. It's going to take as an input the score from judge 1 and the score from judge 2, and it's going to have another linear boundary, and that's going to be the output at the end. So this is how it may look like. So before we pass the score to the judge, to the final, so the president, basically, each of the scores from the judge need to be normalized. So we take these decision boundaries and we turn them into, for example, probabilities. So we go from a linear boundary, we go and normalize a score to go, for example, from 0 to 1. For example, we can use a sigmoid function to go from a raw score to a probability from 0 to 1. And then finally, the formula for the president is gonna combine the score of the normalized score from judge 1 and the normalized score from judge 2 into a linear score. So the judge is going to multiply the score of, the president is going to multiply the score of judge 1 by a number and the score of judge 2 by a different number, and that's going to be the score of the president. So basically what a neural network does is that you're going to, so judge 1 is going to do a linear transformation of the inputs, and then is going to apply a nonlinear function to have a score. Judge 2 is going to have a linear transformation of the inputs and is going to apply a nonlinear function to get a score. The second layer is going to take as inputs the scores from judge 1 or judge 2 and is going to apply a linear transformation to that to get a score. So here is an example on how we could do this. So this is completely an example. So the judge 1 is going to multiply the exams by some number, the grades by another number, and then it's going to sum a bias. And it's going to take a sigmoid of that. Judge 2 is going to do something similar, but with different numbers. And it's going to take a sigmoid of that to get a score. Now, judge 1 has a score, a number between 0 and 1, and judge 2 has a score, a number between 0 and 1. Now, the president is going to take these scores and multiply them by some numbers, in this case, -2 and 2, and it's going to take a sigmoid of that. It's going to plus some bias and take a sigmoid of that, and that will give a probability, and that would be the probability of a person being admitted. So this is a neural network. So let's talk about neural network language. So the input variables are gonna be the input layer. The intermediate scores from judges are gonna be our hidden layer, and the score from the presidents are gonna be the output layer. Now, you can have more than 2 judges, you can have 3 judges. So the hidden layer can have more than 2 neurons. This is what these judges are called, neurons. You can also have more than 2 input layers. So you can have as many variables as you want. Now, you can also have more than 2 outcomes. And in that case, what we're going to have is I'm going to have a neuron per output. So when the output is binary, we just need 1 neuron because you just want a probability, so just one number. But when we have a multi-class classification problem, for example, in which we want multiple outcomes, like 3 or more classes, then we're going to have multiple neurons in the output layer, like in this case for bird, for cat, and dog. We can also have deeper layers. So instead of just having one hidden layer, we can have kind of multiple hidden layers. And finally, I wanted to mention that neural networks are very flexible functions that can approximate, in some sense, any function. Even a neural network with one hidden layer can approximate very complex functions. Thank you.